Okay, in this video, we are going to be looking at the reactions of glycogenesis. Glycogenesis is simply glycogen synthesis. Now the question then is, what is glycogen? The two main organs, cell types, that will be performing these reactions are liver and skeletal muscle. Both of these organs synthesize large amounts of glycogen. And the reason they do this is primarily to store glucose. So glycogen synthesis is basically storing the form of glucose in a molecule that can be accessed later during deprived negative energy needs. So under the conditions of high energy, so for example when the liver and skeletal muscle have oxidized as much glucose as they can to generate as much ATP as they can, they don't want to waste any more glucose that might be remaining in the bloodstream. So they will take up this glucose and store it for later use as glycogen. Now let's take a look at the two different organs, slightly different activities that both of these organs have in glycogenesis. And let's start with skeletal muscle because that's the easier one. Now recall that in the fed state, we have high insulin concentrations in the blood as a result of high glucose in our blood stimulating the beta cells of the pancreas to secrete insulin. The insulin then will bind to the insulin receptor on skeletal muscle, and this will cause a translocation of GLUT4, the glucose transporter, number 4, from intracellular stores to the cell surface. Once this occurs, the glucose that is available in the extracellular space of skeletal muscle and coming from the bloodstream can now be transported inside the skeletal muscle cell. Now recall the first reaction that occurs once glucose enters the cell is the phosphorylation of glucose on the number 6 carbon to form glucose 6-phosphate. Recall the enzyme that does this is hexokinase. Hexokinase, of course, is the enzyme paired with GLUT4. Now, what we've seen up to this point is that glucose 6-phosphate can then proceed on to glycolysis, and the next step is conversion of the glucose 6-phosphate into fructose 6-phosphate. And recall the enzyme that does this reaction is phosphoglucoisomerase. Now a key element of this enzyme, recall, is that its standard free energy is fairly close to 0. So this is a readily reversible reaction. Now the next step is the conversion of fructose 6-phosphate into fructose 1,6-bisphosphate. So these are simply the first couple of steps in glycolysis. The enzyme that performs this reaction is phosphofructokinase 1, abbreviated PFK1. Now, also recall this is another phosphorylation event, and so like this reaction of hexokinase, this is going to be using a molecule of ATP. This ATP is providing the energy to phosphorylate the number 1 carbon on fructose to give us fructose 1,6-bisphosphate. Because these two steps require ATP to provide a large free energy change, these two steps, the hexokinase and PFK1 steps, are irreversible. Now, as we progress through glycolysis, the ultimate goal of this is to generate ATP. Now recall that the ATP concentration in the cell increases because of oxidation of glucose and the generation of NADH going through oxidative phosphorylation, and so we can produce very large amounts of ATP. Now in the fed state, with insulin stimulation, we have a lot of glucose coming into the muscle cell. What this is going to indicate is that we are having a lot of substrate for generating ATP. So our ATP concentrations under these levels will be very, very high in the fed state. Now recall that elevated ATP levels can inhibit the activity of PFK1. This is an allosteric inhibitor of PFK1. So as PFK1 becomes more and more inhibited because of the increase in ATP concentrations, the concentration of fructose 6-phosphate is going to increase. This is going to increase because it is a substrate for PFK1, and PFK1 is inhibited, so we cannot pass this irreversible step. Hexokinase will still be taking glucose and processing glucose as glucose 6-phosphate because recall GLUT4 is a high affinity transporter. And so as long as this transporter is on the surface of muscle cells and there's glucose available in the extracellular space, glucose will be taken up. This reaction keeps going. This reaction is blocked. So that means that this direction becomes our predominant direction under high ATP conditions. So remember our substrate product relationship. As this concentration rises, the reverse reaction becomes more likely because now we have a negative delta G, negative free energy change moving in this direction. The hexokinase reaction is irreversible. So we cannot take glucose 6-phosphate and move it into glucose and send it back out of the cell. The skeletal muscle cell doesn't want to do that anyway. It wants to store it. So now what we're going to do is we're going to have a branch point beginning at glucose 6-phosphate. And it is this branch that is going to form glycogen. So in essence, in the skeletal muscle, the overall idea of this is that under fed conditions, we have lots of glucose in the circulation. Skeletal muscle wants to take that glucose up because of this high affinity transporter, GLUT4. The primary objective is to pass through glycolysis, TCA, and oxidative phosphorylation to generate ATP, lots of it, for the muscle cell. But once this ATP level goes high, we have very little ADP left to convert to more ATP. So now the rationale of the skeletal muscle is to say, let's store this, any glucose that's left. And it does so by responding to the intracellular charge being high, inhibiting PFK1. So essentially, this is the gatekeeper of glycolysis. If we inhibit PFK1, now the substrate of PFK1 increases its concentration and becomes the substrate for the isomerase reaction to reverse. Glucose 6-phosphate now concentrations rise because the hexokinase is irreversible, and now we can enter glycogen synthesis. So what about the liver? The liver is another major storage organ for glycogen. The liver is a little different, that it has not GLUT4, but it has GLUT2 on the cell surface. Recall that GLUT2 is a low affinity transporter of glucose. So the only time GLUT2 primarily will be taking up glucose in the liver cell is during the fed state. This is not responsive to insulin. It doesn't have to be, because what we are looking for is a high level of glucose concentration in the blood due to being in a fed state. And now we've surpassed the Km of the GLUT2 transporter, and so under these conditions, glucose is taken inside the liver cell. In a similar fashion, we have glucokinase is our first step, and we are going to be phosphorylating glucose on the 6-carbon, gluco-6-phosphate. This, of course, is an irreversible step because we are using hydrolysis of ATP as the energy source. And very much at this point, like skeletal muscle, we will be converting this by the isomerase activity into fructose 6-phosphate. The next step is to fructose 1,6 bisphosphate, and again this is the same PFK1. Same considerations as skeletal muscle. We continue primarily through glycolysis, generating ATP beyond the TCA cycle, oxidative phosphorylation, and when these concentrations rise sufficiently, we inhibit PFK1. By inhibiting PFK1, we take advantage of the reversibility of the phosphoglucoisomerase enzyme. And again, glucokinase reaction is irreversible, so we cannot go backwards. So the glucose 6-phosphate concentration starts to build. The purpose of this then is to shunt this into glycogen synthesis. Okay, now let's take a look at the reactions that we are doing to go from glucose 6-phosphate to glycogen. So the glucose 6-phosphate is in its hexameric form. Here is our glucose. We have our number 6 carbon with a phosphate on it. We have the remaining hydroxyl groups of glucose. So this is glucose 6-phosphate as it looks in the cell. Now the first step that we are going to take with this reaction is the enzyme called phosphoglucomutase. Now this is different than the isomerase. An isomerase converts an aldose to a ketose and backwards from a ketose to an aldose. A mutase enzyme specifically is going to be moving functional groups from one portion of the molecule to another. So in this case, we are going to take glucose and it will look like this. Notice what we've done is simply move the phosphate group from the number 6 carbon to the number 1 carbon. So that is the purpose of phosphoglucomutase, and this is the first step in glycogen synthesis. So in this case, we are making glucose 1-phosphate. Now the sole purpose of this reaction to move the phosphate to the number 1 carbon is to prepare it for what we call the charging reaction. So the charging reaction now is that we are eventually going to be adding this glucose monomer to a long chain of glucose polymer, which is called glycogen. And so when a small molecule needs to join on with a larger molecule, the general theme is that the small molecule must bring the energy to join the group. And so next step is to charge this molecule with a high energy intermediate. And what we're going to use for this is not ATP, but UTP, uridine triphosphate. UTP is a high-energy intermediate, also similar in energy levels as ATP, but UTP is the energy molecule of choice when we are performing carbohydrate biochemistry. So in order to link the glucose monomer up, we're going to be adding the charge from UTP onto glucose 1-phosphate. So recall we already have 1-phosphate here. What we are going to be doing is actually taking a portion of the UTP molecule and linking it to the phosphate. So we are actually taking UMP from UTP and attaching it to the number 1 carbon phosphate. What's left are 2 phosphates linked together. Because recall, UMP has only 1 phosphate, UTP has 3, so there's 2 phosphates that are missing in this reaction. So the product of this reaction is called UDP glucose. The enzyme that performs this reaction is called UDP glucose pyrophosphorylase. Now this is a very unique enzyme that it not only adds the uridine monophosphate onto the glucose 1-phosphate, but it has a phosphorylysis activity. What that is going to do is cleave these 2 phosphates into 2 inorganic phosphates. When this happens, this provides us with a very large free energy change, negative free energy change, which is going to ensure this is not reversible. So this hydrolysis of this extra phosphate bond is going to provide the energy to make sure this reaction goes to completion. So now once we have our UDP glucose, now we have the monomer charged with high energy phosphate bonds that can be used for energy, free energy to drive the next reaction, and now we can start synthesizing glycogen. So glycogen is simply the addition of UDP glucose to the growing chain of glucose polymers. I'm going to draw an abbreviated structure here. And what I'm drawing here are essentially glucose monomers, and these are linked by alpha 1,4-O-glycosidic linkages. Now this should be familiar to you because we've seen the same linkage in starch. So now, if we have a long polymer of glucose, we are going to be adding this UDP glucose to the number 4 carbon of the growing glycogen chain. Here's our number 1 carbon. We'll be adding it to the number 4. So this will be added in again, the alpha 1,4 linkage. In doing so, we will be releasing from this reaction UDP. So there will be no phosphates linked up in the glycogen molecule. This whole group of UDP, uridine diphosphate, acts as the leaving group and provides the energy to drive the growing chain growth. Now, there's also, sometimes you might think there might be a chicken or the egg thing here. How do we begin a glycogen chain? What is the first step in order to get this going? Well, we have a protein at the very end linked to the number 1 carbon of an initial glucose monomer here. And this molecule is a protein called glycogenin. Glycogenin has enzymatic activity that allows the synthesis of a few residues of glucose to begin the chain formation. The enzymatic activity of this is the same as what links these monomers up, and it's called glycogen synthase. Glycogen synthase activity. So the same type of activity that links these monomers using UDP glucose onto the growing chain, onto the number 4 carbon of the growing chain of glycogen synthase activity, the same activity this particular protein has. So once a few residues of glucose are formed from this activity, then the soluble form of glycogen synthase enzyme can come in here and then begin extending out this chain with the substrate UDP glucose. Now the other issue we have is that if we have one growing polymer of glucose, and let's say this is our glycogenin on the end of it, we really only have one end to be adding on additional monomers of glucose. This is a very inefficient process, and because we want to store glucose as much as we can into a glycogen structure, what we need to do is branch this structure. So what that means is that when there are a few glucose monomers that are available that have been linked up, let's say these 3, there is a specific enzyme that can hydrolyze the alpha-1,4 linkage between these monomers and take this portion and move it over into forming a branched structure. This branched structure is linked by an alpha-1,6 O-glycosidic linkage. Recall again, this is the same type of structure as starch. So now what we've effectively done is by hydrolyzing this and forming a branch structure, now we have 1, 2 number 4 carbons available for the addition of additional monomers. So we've taken a single point and we've doubled it of where we can have growing chains of our glycogen. Now picture lots and lots of branches, and what we've done is we've opened up the molecule to have lots of addition points. This enzyme is called a branching enzyme. You might also see it named as a 4,6 transferase enzyme. This simply designates that we are transferring this bond of alpha-1,4 into a branch structure of alpha-1,6.